So in this section, we're talking about the solid state and the liquid state. We'd formerly talked about the gas state in which the molecules are really, really far apart. Now they're getting close together, and they're getting close together by attractions between either the ions that make up that compound, in the case of an ionic compound, or the molecules that make up that compound in the case of molecular compounds. Now, whether it's an ionic compound or it's a molecular compound, the name for those attractive forces are different, okay? If it's an ionic compound, we talk about lattice energy. And if it's a molecular compound, we talk about intermolecular attractions. So we're going to have a unit right now on lattice energy, and then we're going to have 3 units on the different terms for the intermolecular attractions. But in all cases, in every single case, it is an electrostatic attraction. What does electrostatic attraction mean? Opposites attract, okay? Opposites in charges attract. So positive charge is attracted to a negative charge. So in an ionic compound, it's easy to say those opposite charges. In a molecular compound, it's not quite so easy to see. But all attractions, to when you get things in the liquid and the solid state, are electrostatic attractions. We're going to see as we proceed that electrostatic attractions are all driven by what's called Coulomb's law, okay? We're going to be looking at Coulomb's law, which is a mathematical relationship with the charges involved there. So let us proceed and let us define lattice energy. This is a diagram to show you what lattice energy is. We start off with an ionic compound on the left, and it's a solid. So we have this ionic compound right here. Okay, and now what are we doing? We are separating out. We are pulling all of those ions apart. Disregard the little red arrows in the middle. We're pulling all those ions apart so they're gaseous atoms independent of each other. The energy required to do that process, and it's required because these are attracted by electrostatic forces, opposite charges. We have a Cl minus being attracted to an Na plus all over the place. And to pull them apart requires energy, and that's the definition of lattice energy. Lattice energy is an enthalpy change. How much energy, enthalpy change is required to do this process is called lattice energy. Now the weird thing about lattice energy is different textbooks define them differently, okay? This textbook is defining lattice energy in this direction, starting with ionic compound and pulling them apart. Some textbooks define it as the opposite process. It would be the energy released when they come together. I like this one better. I like defining it as the energy required to pull them apart. Okay, so if you look at the definition of lattice energy, would you say that lattice energy, as defined this way, is positive in value, or is it negative? Is it a positive sign or a negative sign? Well, hopefully you picked positive. Why is it positive? Because it's the energy required. It requires energy to do that process. So let's think about that just a little bit, review our minds about delta H. If this is the energy of the ionic compound in its solid state, so we have our cation connected to our anion, which is connected to our cation and going off in all directions. If we want to pull them apart, we have to put in this much energy, okay? This is the delta H. We're putting it in order to have them in the gas phase. And delta is final, big energy, minus initial, little energy. Big number minus a small number is going to be positive. So whenever it requires energy, it is a positive change. And so that's the answer to that question. Now, what we have here, and nothing that you need to memorize, is a table full of lattice energies for various ionic compounds. And I want you just to study this table and see if you can find some trends in it, okay? Ignore the melting point part for a moment and look at those compounds. Now, the two things that drive Coulomb's law are the charge of the ions, which we'll look at in a minute, and the size difference between those charge centers. And that's the part that we're going to look at right now with this clicker question. All right, so as you look at those values, would you say that larger charged ions results in larger lattice energies, or would you say smaller charged ions result in greater lattice energy? Okay, now what do I mean by greater and smaller size charges? Okay, so for example, let's just pick one, MgCl2. Magnesium has a +2 charge. Chloride has a -1 charge. I know there's two of them. That's what makes it a good neutral compound. But the Mg2+ is being attracted to a Cl-, and it's being attracted to another Cl-. It's this attraction here between a +2 and a -1 charge that we're considering in this case. If we had something like MgO, this is magnesium with a +2 charge attracted to O with a 2- charge, I would consider that bigger charges than this. You see what I'm saying? They're absolute values. These are bigger charges than these charges. And then we could have Na+ with Cl-, and sodium chloride, where you have a +- charge being attracted together. This would be the smaller. So these are small charges, a little bit bigger charges, biggest charge of all. So which one affects the lattice energy? Which one is true? Okay, so I hope you picked A there. The larger charges result in larger lattice energies. Let's examine closely our table. All of these guys, all of those guys have a +1, -1 charge. These guys have a +2 with a -1 or a +1 with a -2. Same size magnitude. This is a +2 with a -1. So my small charges have these smaller lattice energies. These little bit bigger charges have a little bit bigger lattice energies. There we go. The biggest charges of all have got the biggest lattice energy of all. So it would be, whoops, going the wrong direction there. I don't know why I have that there. The larger the charge, the greater the lattice energy. We can say that for certain. All right, let's move on to the next one. Now the next one has a little bit mess up. I'll skip over that. Let's look at it again. Let's turn all those into plus signs. Hopefully yours are plus signs in your notes. But the next thing I want to look at is the size of the ions, okay? I have a whole bunch of guys here. I want to compare different sized ions. Let's look at these two guys. We have a +1 with a -1, so their charges are the same, but something's affecting their lattice energy, and that is the size of the ion itself, okay? F is higher on the periodic table than Br- is. And as we go down the periodic table, the ions get a bigger and bigger radius. Okay, so the bigger the ion, the smaller the lattice energy when you compare these two. This is a small ion, small F- versus a big Br-. The big Br- is resulting in a smaller lattice energy. So let's see what's going on here, and this is where we're going to see the full brunt of Coulomb's law. Coulomb's law is what always drives electrostatic attractions. And in the numerator, we have the size of the charge, and the denominator is the distance between the charges, which is driven by the size of the ion. If the ions are small, then they're closer together. If the ions are big, then they're further apart. So because of Coulomb's law, there are two things that can help us determine the magnitude of the lattice energy if we did not have the tables. The first thing we look at is the size of the charge. And this is the bigger of the two, and we would always look at this first. Okay, look at this first. The size of the charge. The larger the charge, and I'm going to take out the more exothermic statement and make it more simple, because it's not exothermic in the way our book defines it. The larger the charge, the greater the lattice energy. Fix that in your notes, okay? The larger the charge, the greater the lattice energy. So these numbers get bigger, this is going to get bigger. The second statement is the size of the ions, and that has to do with the denominator. And you'll look at that trend second. So you look at the size of the ion. The smaller the ion, again, the greater the lattice energy. The larger the lattice energy is going to be. So we look at those two things to be able to figure out the lattice energy without the table. Now I'm putting stars everywhere because for some reason students write this down, they put it in their notes, and they never look at it again. And you have to look at it again. You have to know these things in order to answer questions that I present to you. All right? So if you're running across an ionic compound and they ask questions, you ought to be able to answer them. And let's see this next trend. All right? Sometimes I'll ask which one's got the greater lattice energy, and you'll just look at those two statements. Sometimes I'll ask about melting points, so we need to see connections between lattice energy and melting points. So you're looking at your table again. Okay, let's see if the table's on this side. Yep. We're looking at that table again, and we're trying to see if there's connections between the lattice energy and the melting points. In general, if you have small lattice energies, what can you say about the melting points? And if you have big lattice energies, what can you say about the melting points? Well, I'm going to go back to the question and then stop and let you figure it out. Well, hopefully you saw as a general rule, it's not exactly, but as a general rule, the lattice energy increases, the melting point increases. Let's look at it again, okay? Let's pick some. Here we have, let's compare these two guys. We see that the small ion gave me a big lattice energy compared to this guy, and the big lattice energy resulted in a larger melting point. So as the lattice energy went up, the melting point went up. Let's compare maybe KBr and NABr. Na is smaller. We recognize that it should have the higher lattice energy, and it does. It should have the higher melting point, and it does. We see that connection. Let's compare small charge, which is all of these guys, to our big charge. Big lattice energy, okay, they generally result in big. This one doesn't even have a good opportunity to melt, but generally you have big melting points with those. So, here is the culmination of all of this information. I would expect to hand you some ionic compounds and say, rank these from lowest to highest melting point or from highest to lowest melting point. And to do this, you need to remember our connections. Let me grab my marker here. What kind of connections have we come up with? We've come up with the fact that lattice energy, if it increases, that melting point increases. Those tie together. As one goes up, the other one goes up. All right, so that's what we have. We also have got these connections. How do we know that lattice energy goes up? Lattice energy goes up when the charge goes up. Okay? The charge of the ions, let's put it at that, ions. As the charge of the ions increase, we know that the lattice energy increases. And we also know the size, and that's radius, of the ion decreases, the lattice energy increases. So if I'm comparing two ionic compounds, I can compare their size and know which one's got the greater lattice energy. I compare their size and know which one's got the greatest energy. I know I look at this one first, and then I would look at this. If those are the same, I could go to this level. And once I've ranked their lattice energies, I can rank their melting points. So let's look at the compounds I'm giving to you. I'm giving you these 4 ionic compounds. I'm asking you to rank them by melting point. I'm giving you the cue not to look at the table of lattice energies and melting points. If you do that, it's a useless exercise, okay? Because I won't give you the table on the test. So try to rank those by their knowing what you know here, to figure out this. And then once you've figured out this, you can rank them according to their melting point. Now, I can't stop you from looking at the table, and I would recommend you try it, and then you could look at the table and see if you're right. And if you're not right, scratch your head and try again using this information and see if you get it right. This is an exercise in learning, not in just getting a grade. So see what you come up with, and then we'll resume and see how you did. Well, if you struggled and struggled and you worked and worked and you finally figured it out using this information, you would come up with this, okay, which you could have checked with the table. Now, if you didn't come up with this, or you can't figure out how in the world you could come up with this, first thing that I would do is I would go through and look at these to rank their lattice energies. And I know I would look at the charge of the ions first. So if I go through and I look at those 4 that are written up at the top, and I'll just rewrite them here so I can talk about them a little bit. MgCl2, I know the first thing I want to look at is charge. So magnesium is +2, chloride is -1. The next one is LiCl. This is +1 with -1. The next one is NaCl. This is +1 with -1. And CaCl2 +2 with -1. So at this moment in time, I can know that this has got the larger charge and this has got the larger charge. So they would have the greatest lattice energy and the greatest melting point. So I could put them down here. I don't know which one's biggest yet, but I know I would put them on this side of things, CaCl2. And then I would put these down here, LiCl and NaCl, simply because big charge means big lattice energy. Big lattice energy means high melting point. Low charge means lower lattice energy, which means lower melting point. Now, how am I going to further distinguish them? Now I look at the size of the ions, and I compare the size of the ions. Li, and I've got a periodic table over here that I'll circle those ions real quick. We've got Li and Na and Mg and Ca, okay? So we're looking over here with the Li and the Na. Li is smaller than Na. It's closer up on the periodic table. So this is smaller. The smaller the size, as it goes down, the lattice energy gets bigger. So this is going to have a bigger lattice energy because it's smaller than this is going to have. So between these two, I can differentiate them a little bit more. I knew they were smaller than these guys, but now I can say that this has got the smallest lattice energy of all. And if it has the smallest lattice energy of all, it's got the lowest melting point. And we see that we had that one ranked first. Okay? Then the next one will be the lithium chloride. Can't really see that Cl very well. There we go. So we've got the lithium chloride. We got those two listed first. Then we get over here and we know that they were bigger lattice energy, so bigger melting points. But how do we further differentiate them? We saw that the magnesium is higher up on the periodic table. So magnesium is a smaller ion. So it is, as the ion size gets smaller, it has the greater lattice energy of these two. Okay, if it has a greater lattice energy of these two, it's going to have the higher melting point, and so we see it listed last. So that's the thinking through that you have to do in order to work this problem. You're going to run problems like this on your homework, and on the exam, I'll throw out some ionic compounds and say, rank them. A lot goes into this. And historically, students do terrible on this, but I'm hoping I have tweaked this lecture a little bit and make you think about it, and you'll be able to rank ionic compounds using this information. I think that ends this lesson. Yes, it does. So, ionic attractions between ions is an electrostatic attraction. It's what holds ionic compounds together, making them the solid, and we can rank their melting points with this information.